All right, let's start. Topic for today is learning for writing the shellcode. So what that means is like we are actually writing something similar to get a shell function. I told you that none of the developer would intentionally put that kind of code in their code. In that case, like we can inject that and then run it. So like we will basically learn that kind of method in this week. And before learning that, we need to go over some of the logistics and recap. So due date for week 2 challenge sets were passed. So there will be 50% penalty, but I know some of the students like join late and then like some of the suffering about some of the circumstance, and then they are exempt for that penalty. But the important thing is like that after February 6th, there will be no point. I need to push you guys to like do all the work before we move forward. So that's why. And then for the extra credit challenges, right now I set the due date as March 8th. So you will have plenty of time. So, and then the reason why I set that long time is like as you learn more about week 3, 4, 5, 6, then like you will feel that those extra challenges are easier than you expected. So yeah, I want to give you the chance to solve, and then like get excited about like at the moment you get the flag and then submit that. Yeah. Any questions for the due date and the next challenges, or no? Clear? Great. And then let's do a little bit of recap about what we learned about the buffer overflow. So it's very simple. So I told you computers are very dumb. They are just running how it is written in the code. So they're not creative, but we are creative. So that's why we can overflow the buffer and then directly overwrite the Ghetto shell. Then we can make the program run different thing, and we can do whatever we want to do. And then we also learned about the frame pointer attack. So for these kind of stack, we call these like a green part as a pure data. And then these somewhat cyan part, colored part, we call that as a control data, because that affects to the program's control flow that matters for that. So if we can change any bit or byte in the return address, then we can easily change the control flow of the program from the expected one. And also even for the frame pointer, because it will indirectly can point to entire stack to the entire different memory regions. So we can change the control data there. So in the security research community, we regard these part as a control data. And then what could be the easiest way to block this kind of the buffer overflow attack? Can you suggest a very simple way? Yes. Oh, that's good. But that might be super inconvenient for the usability. And then you pointed it very well. So for the security research side, we always go through like a usability and security debate. So if we go for the 0 usability, then we could have 100% security. So the best security is to plug off your Ethernet cable. So that's the thing, right? Yeah. So not that one. Little one step forward. So what could be the easiest way to defeat this kind of attack? Yes? That's also good, but that's a fundamental defense. Yeah, it's conceptually it's easy. Yeah, but yeah, right. So that's right, but you are one step ahead, because what we will learn is actually like writing the shellcode and then execute on the stack. But we have not put any kind of code on the stack and execute it yet, right? Right? Yeah, something similar to that. That's what I was expecting. So I think that's the correct answer. So what I was waiting is like why do we put the control data and then regular data in the same stack? We can actually split that. So for all the control data, we can put return address, frame pointer, and the separate stack. Suppose we have 2 stacks, and then put all the buffer and the others on as a data stack. then no matter what you overflow on the data stack, you can never hit this point. Yeah. So that kind of the construction is possible, and then everybody wanted to like have that kind of environment on the across all the operating systems. So that kind of thought was like the coming out around like the 1998, 9-ish, but that was implemented recently with the starting from the 12th generation of the Intel CPU. So if you don't know about this, please search about Intel CET, control flow enforcement technology. Yeah, they are actually implemented the two stack. So the one is the data stack, and the other is a so-called the shadow stack, and then store all the return addresses at there. And then even if you change the return address on the regular stack, they will honor this value, and then like the hackers can never touch those kind of area. But the important thing is like that although that kind of thinking is very simple, implementation of that took like around 25 years. Yeah, so that's the like the security business and then all the stuff. Yeah. So yeah, so the important point is like we don't have to put like these kind of control data at the same time on the stack. Yeah, but we will cover more sophisticated defense later. But I just want to give you a hint and then think creatively about like the we can have a very easy and naive thinking, but we can completely kill the attack. Yeah, that's the point. Any questions about that? So are you all agree that the splitting that is very simple, right? Yeah. No? Yeah. And then like the important thing that we learned is like by altering the frame pointer, we can change the entire stack. So because the code is fixed, it will run as expected. So if we match all the data like this, leave, return, then we can return to anywhere. Yeah. And then like that, I put like some of the rule of thumb or a formula kind of thing, like you need to put the buffer address and then that +4 will be the return address. But I don't like that kind of the formula exist. And then like what I wish is like you can always think and then figure out that. Yeah. So please don't rely on that kind of formula. But after you practice sometimes, then please think always that if there's a little bit of logic at there, you can analyze that, then you can match the data and solve the challenge. So that's actually embedded in like the buffer overflow challenge level 9. So maybe you don't agree. How I feel is like that is very similar to the frame pointer attack. And then I believe like some of the students who already solved that challenge will feel like that. Yeah. Yeah, I know that some students are like saying like, oh, I spent several hours, I cannot get it, even if I get like a 5, 6, 7, 8 in 30 minutes. Yeah, but that happens. But after you understood that correctly, then you will realize that the buffer level 9 is not that different with the 5, 6, 7, 8. Yeah, that's the point. And I put some of the useful lines for the pawn tools here. So please refer to the slide and then use those kind of the functions whenever you need to take a look at the core file or others. So whenever we have a crash, it will generate a core file for you. And then the core file will have a exact state. State means that registered in memory at the time of the crash. And then you can take a look at the environment using GDB, or you can also programmatically interact with core file using the pawn tools core object. So one of the things you might want to do is like after you put some of the thing on the stack as a buffer, you want to find where it is. And then to do that, you can easily find that using core stack.find. And then in that case, if you put a lot of A's, then like if you find 8 A's or something, then there will be a lot of places for that. But if you use a cyclic function, I told you that the cyclic function will generate that quadrat of the bytes as a unique one, so that you can easily find the start of the buffer by using that. And then for students who are not familiar with the TMX Pontos GDB, then please refer to some of the cheat sheets or like the available resource online to get familiar to those tools, and then that will speed up your exploit writing a lot. Any questions up to this point? All right, then let's move forward to learn about shellcode writing. Before we get to the shellcode, let me explain like what we need to do for like successful exploitation. So I designed the week 2 challenge sets to be very easy. So what you need to do is just change the return address of the Ghetto shell. And then to get through all the steps for the vulnerability exploitation. So the first step to like the writing an exploit is like you need to identify where the vulnerability is. So in the challenges for week 2, 3, 4, 5, 5, and up to week 5 challenge sets, I believe you don't have to worry too much about finding the vulnerability, because the vulnerability will be all same. Yeah. So there is a read or apt-get function, and then they're always like the buffer overflow. So for example, if you take a look at this assembly, there is an apt-get function, but the buffer is coming from EBP minus 0x80, which is like a minus 128. That it pushes the second argument is a C0, which is 192. Yeah, definitely 64 bytes overflow, right? Yeah, that's the case. But so what I mean is like up to week 4, you don't have to worry about where the vulnerability is. It's very imminent and there is. Yeah, but we will practice later about the finding vulnerabilities in week 7, and then in class CTF at the week 9. Yeah. So like let's put that back there, but you need to know about like the most important part is like we need to find the vulnerability first. But after you find the vulnerability, you need to analyze the distance of the buffer to the return address, and then fill the buffer accordingly, and then point to the function that you want to run. But here, we will learn about resolving the last step, this last step. So not just for finding the vulnerability, not just for analyzing the program to trigger the vulnerability to take control, you need to have somewhere you can execute and then get the privilege and then take the control. And that was summarized as the Ghetto shell in the week 2 challenge sets, but starting from week 4, there will be no such functions. But you still need to execute equivalent functionality of the Ghetto shell. And today we will learn about how we can write that and inject that to the program. So, simply we change the return address to Ghetto shell, then we can get the flag. But usually the programs never have that kind of the code. So if there is no such function, then easiest way to work around is writing our own thing. Yeah, that's simple. Yeah, and then we can create one. And to do that, we need to know about like what the Ghetto shell function do. And let's take a look at that. So this is the Ghetto shell function, and you will see that there's a printf. Then you can ignore that because I put that as an indicator that you successfully like own the program. Yeah. And then the important parts are like these 2 functions. Actually, it calls the 3 functions: get EGID, set regid, and execl. And I explained about some of the group privilege. And then the reason why you cannot read the flag is like this flag is only readable by the owner and group for this kind of the group ID, but your ID will not have the GID. And then marked with this yellow color, and then there's a S sticky bit on the executable part of the group. that means that while executing this program, the privilege will be with the group ID, and then not your group ID. That's why you cannot attach GDB while you are running this program, because that is completely in the different world in terms of privilege. Yeah. So what we need to do first is that before running the shell program, we need to inherit the privilege. And to do that, so this functionality, set ReGID, that means the set real and effective group ID as these one, so real and effective. But what we are doing is like we just set the real and effective group ID as the effective group ID. And then effective group ID means like this one. So while we are running this program, our effective group ID will be this one. And then we would like to replace our privilege with that. That's the meaning of this function. Yeah. So you can put the group IDs are just number. And then I also put the numbers here. Yeah. So if you want to prepare just using this kind of number, you can use that. Yeah. And then for some of the challenges, you can make the things easier by just putting that kind of the group ID number. Yeah. But that means that that functionality can only work to specific challenge, because challenge will have a different group ID. But we will learn about the general way to write the Ghetto shell functionality. So no matter what kind of group ID there, then we can check the current group ID and then set that as our real and effective group ID. So thing is, we need to call get EGID first, and then set that as a group, our real group ID as a set ReGID. And after inheriting the privilege, we need to execute the shell program. And then the reason why execute shell is like after getting a shell, we can execute any other programs. So this kind of the attack is called as a arbitrary code execution, because after running shell program, you can execute any kind of program. So that's conforms to the arbitrary code execution, right? So that's why. And there are several functions that we can invoke to execute the program. So one of the example is like in the C library, there's a system function. We can use that. And also we can use execl, exec list. So we can provide it as a list. Exec vector, we can provide the argument as a vector. Vector means a array. And then exec ve means exec vector argument and environmental variable. So this function gets like 3 arguments, target file path, argument as a vector, environmental variable as a vector. And then we will focus on exec ve, because the difference between the difference in like the exec ve then like the other these functions are exec ve is a system call. What that means is that the operating system opens an API for the programs, so that we can if we invoke this function, it will directly talk to the operating system. But for these other functions are C library function. So your program calls that functionality, and then internally C library do some of the things. Actually, if you provide the list or something, then internally it will build the argument as an array, and then put the environmental variable and invoke the system call. So there are a lot of things in the middle, but what we will do is like we will directly call the system call, skip everything, and then get the shell, because that will be the shortest path, and then you will have a minimal code in your shellcode. Yeah, that's the thing. And then how many of you have invoked the exec ve in your code when you're developing something? And we have some, but very few. But I believe mostly like you will have more experience in running system function than the exec ve. But the difference is the library call and system call. And then library calls are there for having more usability for the developers, and that's why. Yeah. And then like how we can invoke execve is, so we need to have a path name for the target file to execute. So the most basic shell is at the /bin/sh in the most of the Unix system. Yeah. And then you might think that, oh, what if like if that was changed and then, but practically that cannot be happen because, so if you install Ubuntu or like any kind of a Linux distribution, so there are a lot of scripts. And then most of scripts are assuming that there is a /bin/sh. So if you remove that, and then your other functionality of that system will broke. So you can safely assume that in the most of systems, it's not a special machine, weird machine like that, then you will have /bin/sh as a program. So that you can always set the first argument as a /bin/sh. That's it. But how can you set argument vector and environmental variable pointer? So for that, operating system expects like that there will be array of strings ending with the 0 at the end. And then same thing for the environmental variable pointer. There will be array of the strings, and then at the end, there will be 0. Yeah. So in writing shellcode, or in sometimes you don't have the full control of the program's environment, then you cannot met this kind of the sophisticated condition, because like all the addresses are valid and then ending with the 0 as a string, and then array must be ending with the 0. So it could be too complicated for making exploit. But the easiest way to running execve without any kind of complaint is doing something like this. So maybe I explained too much, but I want to give the full context of the thing, and then I will let you know the easiest way to get there. So we need to get the privilege. So we need to run set regid with the effective gid. And then after that, we need to run execve. But the simplest way to invoke that is like just to put /bin/sh as a string for the path name, and then put 0, 0, the null for the LD array. Then the operating system will, will think that, there's no argument. And then this program don't care about the environmental variable. Okay, it's simple, and just run it. So that this is the easiest combination that you can make, so that we will learn about that. And then like this is a shellcode that I wrote in 2008, I believe. Yeah. And then like at that time I was playing lots of like CTF and war games, and then like this kind of information were not shared. And then I also had a lot of headache at that time writing the shellcode. I really hated assembly at that time. Yeah. So like I spent so much time like having like the one shellcode. I want to use it everywhere. Yeah. So in this case, like because most of the CTFs, they are playing with the user ID. So right now I designed with let you guys playing with the group ID, but there's not that much difference. So that's why this shellcode invokes set re-UID, EUID. But practically, what you need to do in this class is like just changing as a GID and then exactly. And then I use this shellcode for like every other CTF, and then it works well. And then many other hackers just borrow my code, and then still that is like the archived in the package store, one of the like the hackers archive. Yeah, I'm proud of it. And then one of the students, Rudy, mentioned like even before like he like see this slide. Yeah, last night like he messaged me as like oh, I found your old shellcode. Yeah. So if you, and then another thing that I want to tell you is like so after learning how you can write the shellcode, you can also write your own creative shellcode. If you do so, post it like that, then like some other hackers will use that. And then when you go to the conference or something, oh, I don't know you, but I know your shellcode. So that moment will happen. Yeah. And then right now, like some of you think like oh, what's that kind of the esoteric thing? But I believe like after 2 weeks, you will also see that, oh, that's the right thing, and then you know about all the details of the thing. Yeah. So this is a shellcode, and then shellcode is actually like I wrote it as an assembly, but think about it. Assembly language will be compiled into some of the byte stream, and then how CPU read the code is they don't read assembly. Assembly is also human friendly. I know you guys will never agree with that. Yeah. So in the CPU's perspective, it's not friendly to them. And then what they expect is so-called opcode. Yeah. So for example, push 0x31 is like 6A31. So that's the opcode. And then they just interpret those kind of bit inside of circuit and then run the code according to like there's a table, and then like they are running according to that. Yeah. So what is the shellcode is that it's just a byte stream like this. Yeah. And then the syntax is like the \x means like the escape sequence to like to express some of the characters, even if that is not printable. We can put any kind of the hexadecimal number in like the 0 to FF, yeah, to represent the character. And then because like these kind of opcodes sometimes includes like non-printable characters, so the shellcode will be resulting in like the string, but yeah, something like this. And then what we will do is like we will basically put this shellcode into somewhere in the stack, and then we will change the return address to there. Then, have you heard about the Harvard architecture and von Neumann architecture? No? Then I have to ask, like a CS162 include that? So like maybe that's the very old, like the kind of concept, but in old days, yeah, CPUs are, so there's a CPU and then there's a memory, and then to access the memory, we need a real copper lines, yeah, to read the memory, because like all the bits and data and then actually like they're transferred like that. I'm not an electrical engineer, but yeah, it's something like that. But in old days, those lines are expensive. Yeah. So in old days, we have 8-bit computers or something. The reason why we have a limited like a bit or in that way is like that kind of adding line that makes a circuit complex, and then we cannot put a lot of transistors on the chip like what we are doing in these days. So all the things are expensive. And then if we have like the 12 bits for the memory, and then 20 bits for the memory lines, so that kind of thing is like the complexity increased by like the having much more lines. I don't know the exact scale, but it's not linear, more than linear. So that's why we cannot increase that at that moment. So what Harvard architecture means is that, so because having many lines to the memory is complex, so what they did is like that they do have separate memory for code and data. So if they want to use the 20 bits for the addressing the memory, then using the 6 bits to addressing the code, and then using the 14 bits addressing the data, then in that way, like a circuit complexity could reduce down. So in a very old day, code is there, and the data is there, and then no matter what you do, your shellcode will be here, and then all the data memory is never be executable. Yeah. So that was designed in a very old day. And then that design is coming from the Harvard University, and then that's why it's called the Harvard architecture. But the computer and the mathematics genius von Neumann never agreed with that argument. So he developed the von Neumann architecture. And then what it entails is like to put everything in a single memory. Yeah. And then at that time, yeah, that was a little complex to do that, but with the Moore's law and then all the thing, yeah, our engineers catch up all that complexity. So now we enjoy like we have like a 256 bits lines to the DDR4 and 5 RAM right now. Yeah, so it's super wide. And then That's enough to like store all the data and code in the same memory. So that right now we put all the code and data in the same memory. But that actually gave hackers a lot of opportunity. Then there's no distinction between data and code. So we can inject any kind of data and then run it. So that's why this kind of the shellcode execution is available. Because some of the students thought that like oh, this is a purely data. But why the CPU run on that kind of dumb data? Yeah. Then the answer is like they are designed to be that. Yeah. Yeah, that's a little side story, but I want to let you know about the full history about that. Yeah. And then how can you use the shellcode? So after identifying the buffer overflow vulnerability, what we want to do is like overflow the buffer and then overwrite the return address. But what you will do is like after writing the shellcode, you will put that somewhere on the stack and then put that address as a return address, then program will jump there and then run it. Yeah. That's it. And then what your shellcode need to do is these two things. Right. And then let's get into how we can write that. Yeah. So to write that, you need to understand what is system call. So the system call is the API of the operating systems. And then like because like the operating system need to provide like some sort of the security. So all the hardware access or like some of the important resource access, for example, privilege or file access, console access, those kind of things must be mediated by the operating system. Yeah. And then for those who who already take them CS444, you might have already know about that kind of concept. But if you're not, then please take the CS444 later. Yeah, that will give you much more clear idea about that. Yeah. And how we can invoke system call is it's not human friendly because system calls are for library writers, and then they do have a ABI, not the API. Yeah. So that we need to interact with the operating systems, the system called ABI. And how we can do that is, so let me show you a little bit of thing. Share. Share the entire screen. So there are a lot of functionalities in the operating system. So if you get into this website, then it shows that the list of the 32-bit system calls. And then you can choose what function you want to call, not by the name. CPUs or operating systems, they don't know about the name. They love numbers. So how you can choose the functionality is that, so here's a functionality that we are interested in, EXECVE, right? So it says the system call number is 11. In hexadecimal number, that's the 0xVE. And then you need to put this value to the EAX register. Yeah. So if you set the EAX register as 0xB before invoking the system call, that means you are telling the operating system that, oh, I want to invoke execve. That's it. And then execve has arguments. And then how you can pass the argument is that, so in 32-bit, we learned that the library calls are passing the argument using the stack, but the operating systems are not. So they use registers. It's somewhat similar to what 64-bit architecture does. So even for this 32-bit architecture, you need to put this first argument 0, to the EBX register. Second argument is the ECX. Third argument is the EDX, and then ESI and EDI and so on. So the order is ABCD, number at EAX. And then first, second, third argument is a BCD, EDX, ECX, EDX. And then what we need to do for execve is, so we need to set EAX as a 0xB, the system call number, EBX as a /bin/sh. and then dx and dxr as a 0. Then we can successfully invoke running the /bin/sh, and then we can tell the operating system to do that for us. And you can search for any other system calls. For example, if you're curious about get EGID, then that number is a 6C. Is that correct? The 32-bit? Oh, that moves to the 64-bit, but we can, yeah, this one is this 32-bit, 32. Yeah, that's the number for the get EGID, and then we need to call another function set regid, right? So that you can also search for the that number, and then if there's an argument, we can put that on the EBX and ECX. And for 64-bit, there's a little bit of the different thing, but the conceptually is the similar. And I don't know why they completely changed the system call numbering in 64-bit. So exec B is not 0xB, it's 0x3B. Yeah, 59, right? Yeah, that's the exec B. Yeah. So please note that in 32-bit and in 64-bit, their system call numbers are different. So please refer to the slide, or we will use just a few system calls and just memorize it. Yeah, that'll be good for you. And then their argument order will be the same as the ABI of the libraries. So their orders are RDI, RSI, RDX, RCX. They change it. So in our version, that'll be RCX, but in some other distro, they will use R10 for the depending on the kernel. But in our case, that is RCX. Yeah, but we will not use like the fourth argument in the most of cases. So just focus on these three. So instead of using A, B, C, D, then same RAX for the system call number, but their argument passing order is a little different, but that's the same with the library call. And let's get back to the slide again. So we need to call these three system calls. This three, and then like you can easily find the numbers and then like arguments, the information in this side. So that's the thing. Yeah. And then you can also refer to this slide to the argument orders and how you can set that. Yeah. And then after setting the arguments, how you can actually tell the operating system, please invoke this system call is in 32-bit, that's software interrupt with the number 0x80. Yeah, I don't like this kind of the weird details, but in early days, the CPUs are not designed to support the sophisticated operating system. Yeah, so it's more likely softwares are matching to the CPU architecture. So that's why we are using int 0x80 in Linux. And then that number is totally different in Windows. And then Microsoft Windows uses 0x2e. And then in my class CS444, it uses like 0x30. Yeah. So it depends on like how software defines about the software interrupt. But because the de facto standard is like using Linux in the many cases. So you can memorize that as like 0x80 interrupt. That's the thing for like the invoking system call in 32-bit. So how we can invoke the system call is to invoke a get EGID. So we need to set that number. That was a 0x32, I believe. Yeah, and then put that in EAX using the move instruction. And then int 0x80. Then it will let the operating system invoke that function and return. And then same thing applies to here. The return value will be stored into the EAX register. So as a result, the EAX register hold the effective GID, then we will use that. So after running that, we need to invoke set regid as the effective GID as an argument. Then we need to move EAX to EBX because EBX is for first argument. ECX, that's the second argument. we just set those arguments with the return value. And then we will invoke another system call, set regid, which is number 0x47. So we put that value to EAX. So right now I just use a symbol, but you see that this dollar flag, that means the immediate value. So that's not an address, and that's just a value. And then if you take a look at some of the header file, then you will see that the value is just this one. And then after setting all the register values, just run into 0x80. Then your privilege will be changed afterwards. After that, we need to run exec BE. So what we need to set is, we need to set EAX as a 0xB. That's easy. Move 11 to EAX. That's it. And then ECX, EDX is 0. Move 0 to both of registers. But the problem is that, how can you set the EBX as the address of the BNSH? So if we know in your program, there is some of the /bin/sh string, then we can point to that address. But the problem is that we cannot assume that there will be /bin/sh in the program. Likewise, we cannot assume the Ghetto shell function exists in every program. So why the developers would include like that kind of string in their program if they don't use the shell at all, right? There's no reason. So we need to think about how we can build a string in the memory and then put that address on the EBX register. And then how can you do that? Is very simple. We can use a stack. So we need to put the address of the BNSH to EBX register, but all the values in 32-bit machines are like the ending with 4-byte blocks. So instead of using /bin/sh, which is 7 characters, we will use /bin/sh. So it doesn't matter because this slash will be ignored in the operating system. So synthetically, it's okay. But it has 8 characters, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so that makes the things are easy. So that's why I'm doing that. So instead of putting this string, we will put this one. And then how can you do that is, so in binary programs and then something written in C. So Linux kernel is written in C. So they regard string as some of the thing ending with 0 null byte. Yeah. So that we need to have a null byte at the end. And to create that kind of string, we can push 0 first. Then you will have 4 bytes 0 at here. And then we will push n/sh, that value, as an integer. So it's a little endian you need to, like the how can I put it? Flip the thing, to match it. So that this value is actually n/sh, and then push /bi. And if we read the thing from here, then /bin/sh and null. So that's how we can create the string. Yes, a question.
Do a slash at the beginning instead of just adding the 0.
So we will learn that later. And then the important thing is we should not have 0 in our shellcode. The reason is, so sometimes some of the input function requires your input to be a string. So if you have a 0 in the middle of your shellcode, then if the input function is scanf, then your input will be cut off at here. And then the rest of shellcode will not get injected to the program. So the first challenge you will solve is like a shellcode 32, shellcode 64. But right next challenge that I prepared for you is like a non-zero shellcode 32, non-zero shellcode 64, so that you should never have 0 bytes in your shellcode. But you will see that right now we have a 0 at here, but we will learn some of the tricks that they're removing 0 in your shellcode at all. Yeah. So that's why we need to do that, because like if you think like the slash bin slash sh is 0, 0, then we can remove this one and then put 0 at somewhere here, right? So that could be the one of the solution, but that makes like our shellcode to have 0 bytes, and that's why. Yeah. Yes. So we need to let the operating system interpret like that string correctly, and then point to the slash bin slash sh, right? And then we can do many things, and then so instead of adding slash at here, we can also adding slash at this point. Or if you know that there is a different shell, ASH, then you don't have to do that, slash bin slash ASH. Then that's an 8-byte. So the reason is like we need to make it to be 8 bytes, and then that's why I just added slash at that. Yeah. So after doing this, we will set the EBX register as the ESP. The reason is we push, push, push. ESP is actually pointing to this string, so that will fulfill the requirement. Yeah. Any other questions? So if you cannot get this clearly, that's okay, because we will have a tutorial so that you will get more clear when we run on the debugger or something. So I will demonstrate that. Don't worry much about that. And then next is 64-bit. Yeah. So not that different. So to invoke a get EGID, just put the number on RAX. But the different thing here is that, so the 64-bit architecture for x86, I wrote it as this, but that's officially called AMD64 because that architecture is developed by AMD. So AMD just extended Intel's architecture, but Intel wanted to have a totally different 64-bit architecture called IA64. But maybe you've never heard of it because that CPU has been obsoleted. Yeah. So yeah. And then in AMD64, the architecture was developed around the 2001, 2, 3-ish. That means the CPU architecture born after modern operating systems are there. So they don't use weird instruction interrupt 0x80 to call a system call. There's an instruction called system call, syscall. Yeah. So in 64-bit, we will use syscall to invoke the system call. It's more human-friendly assembly, right? Yeah. So that's the thing. And then rest of the things are very similar. But in this case, you will have a 8-byte blocks for push the registers. But the important thing here is that there's no 8-byte push in 64-bit architecture. I know this is very weird. Yeah, there's no so you can always push 1 byte, 2 byte, and 4 bytes, but you cannot push 8 bytes on the stack. To do that, you need to move the value to the one of the register and push that register. I don't know why the architecture is designed in that way, but it is. So we need to do that. So that's the one thing. And then the next thing I need to describe is like as you asked the question about that, we need to remove all 0 byte. That's why we cannot use a 0. So to build a string / bin / sh, we might have like the push 0. And you will also see this kind of the result in later as an opcode. I will show you. So if you write push 0, that will be resulting in opcode as a 680000. Oh, there are 4 zeros. Yeah. In that case, we cannot use that shellcode. Yeah. Because scanf, string copy, or all sort of the string related functions will cut your shellcode at that point. Yeah. And then how you can remove 0 is that we don't have to put the immediate value 0 to have 0. That means you can create 0. Can you see how can we create 0? put some of the random value, EAX. Subtract the same value, EAX. There's no zero at all. It'll have like the, I forgot the opcode, but the 40, 41, 41, 41, and then there will be no zero, but as a result, EAX will have zero. So instead of doing push zero, we can do push EAX. Then it will push zero on the step. And then what most of the hackers are using is actually XOR EAX, EAX. So if you do exclusive OR to the same value, then it'll be always zero. And then opcode for this instruction is 31C0. Yeah, it's only 2 bytes. Yeah, so it's quite efficient. Because
I was going to ask literally this.
You're right.
About echoing register, and then like since that's faster.
Yes. And then there are many other tricks. And then we will have a challenge. I need to show you. So I like code golf. And then I want to play code golf with you all. Share screen. So there is a challenge called the short shellcode 32. And then you need to write either 32-bit and then 64-bit shellcode. But if you make it as shorter than 12 bytes, then you will get this challenge. But I want to go further. So if you get 7-byte shellcode, then I will give it 10 more points. 6 bytes, 20 more points. 5 bytes, 4 bytes, 3 bytes, 2 bytes, and extra credits are doubled. I said it like this because I know it's difficult. Yeah. And then my best was 2 bytes. And then I've seen up to this point 3 students have successfully demonstrated that they can do with only need 2 bytes to nail down these challenges. So please try after solving all the other challenge, because I know that I know this drains a lot of time. I also take like several days to get to the 2 bytes, because like the up to 2018, my best was 3 bytes. But while I was talking to one of the students, at the same time realized that we can do it with the 2 bytes. And then in the class, battle was started. And then, yeah, I won. But I really wish one of the students beat me with the 1-byte shellcode. But I'm not sure that's possible or not. But at least please try like to any of like this thing. Yeah. Pardon? If you do it with 0 byte, and then you can own the world. Yeah, I've tried that, and then like no luck. But there is something other you need to control, and then brute force the entire space is quite difficult. Maybe ask ChatGPT about that. I'm not sure. Yeah. But I know it's difficult. Yeah. And then like to introduce another more fun challenges are like I wrote the challenge that you need to write all the shellcode in ASCII characters. What that means is like right now with the shellcode, we can use any bytes from 0 to FF, but in this challenge, it will be restricted as a 0 to 127, 7F. And then even if we don't use like the rest of the half of the opcodes, we can still do that. And then that's the one thing. And then another thing is this one. So you can technically write your shellcode using only these characters. And then interesting thing is, so I told you to invoke the system call, we need to run interrupt 0x80. The opcode for that is CD80. Then that's actually not in here. Yeah. but you can still invoke the system call. And then opcode is for syscall in 64-bit is 0F05 or something. Yeah. And then that is not in here too, but you can still do that. Yeah. But for 32-bit, it's easier. So I set the challenge as a 32-bit. So if you write the alphanumeric shellcode, you can actually read your shellcode. A, B, C, D, or 1, 2, 3, 4, that kind of thing, right? Yeah. So please try to solve this challenge after solving all the other challenge. That's why I said it as extra fun. Yeah. So please try it. And then for this challenge, I have seen 4 students have succeeded in like the history. Yeah. And then our TA, Lucas, also want to solve this challenge at this time. Yeah. So like please try to think about like how you can do that, but I'll also give like some of the hints for that. Yeah. And then like from these kind of sites, you can see that what kind of the characters are maps to the opcode for ASCII like this, so that you can only use like these kind of instructions. Yeah. To finish that. And also for the alphanumeric, then you have more limited character sets. Like this. Yeah. Then you can still do that. Yeah. I believe the shellcode that I wrote for the alphanumeric is like the 48 bytes or something. Yeah. So I just want to tell you that this is not that complex. Yeah. Trust me. Yeah. And let's continue. So today we will also cover like the non-zero shellcode. So, and after that, yeah, I just introduced like these kind of stuff. So yeah, please keep that in mind and then challenge yourself. Yeah. And these are the little descriptions of the week 3 challenges. And the due date is next Wednesday. We will have a little bit more time than 1 week. Yeah. And before I move to the tutorial, is there any questions on the lecture? And then another thing that I want to tell you is like on Wednesday, so I don't have much things to teach because we will be writing shellcode. Yeah, so the lecture will be a little short, around 15 minutes about that. And then we will have plenty of time to writing a shellcode here. And then myself and Lucas will help that. And I don't know for like the ordering pieces for you. And then do you like it? Yeah. So like in the Discord, I will set an announcement that if you want pizza, do something like this, and then I just want to like how many people will come. Yeah. So the student online, yeah. If you want to have some pizza and then play with the shellcode, please think about the coming to the class. Yeah. Yeah. Then I will also accept like what could be your favorite toppings or something like that. Yeah. Yeah. So I will announce that Discord like maybe later today. So please do this kind of the voting for that. Yeah. All right, then let's start tutorial. So to start with the week 3 challenges, we do the same thing. Fetch week 3, then it will like open all the things like this. Then to write the shellcode, I prepare a shellcode template here. Yeah. So you have a shellcode.s, that's the source code file that you can interact with. And then if you put the assembly lines up there, and then there's a make file, if you build it, then it will build shellcode.o object file, and also the shellcode.bin, the binary file that contains shellcode. And then how you can interact with the challenge is after you're writing the shellcode, you need to put the shellcode.bin into the challenge directory and run it. Because our challenge binary expects to have like shellcode.bin file will be there. So that's how you can interact with the challenge. So I'll show you how you can start the challenges. Like let's solve a shellcode 32 first. And to do that, copy everything from the shellcode template to the current directory. Then you will see that those files are in here. And then we will start based on this template. And then I put some of the important information. So this kind of what we need to do like these. And also for the system call numbers like these. And then some of the steps, and then some of the tips that how you can build a string. Yeah. So how you can do that, how you can play with the shellcode template is like you can just write the shellcode. And let's try to write the shellcode for 32-bit. And our objective is to invoke this kind of thing. And then let's start with the get EGID first. And to invoke a system call, we need to move system call number to EAX. And then interrupt 0x80. That's how we invoke system call. And then we can test that so that don't write everything at once. If you write one step, then try to test it with the debugger. So I just write how we can call get EGID, and then run make. And then it says make 32 or 64. So right now we are playing with this 32-bit one, make 32. Then it will build all the thing. And then there are 3 files, shellcode.o object file, shellcode.bin as a binary file, and then shellcode program. So the shellcode program actually run directly your shellcode, so that's not a challenge program, but you can test if like it runs correctly or not. So first thing you want to check is like how the opcodes for your current shellcode look like. And to do that, there's a program called object dump. And then -d means that you're getting a disassembly. And then shellcode.o object file. Then from the main, so what I did is move this get EGID to EAX, right? And then that's actually B3, B8, 32, 000, and then CD80. And then we will take care about removing 0 later, but just focus on writing shellcode for now. Yeah. So as soon as it will work, and to test that, you can actually run GDB with this shellcode file. Please note that this is not a challenge binary because it will directly run your shellcode. And then what I will do is disassemble on main. So the main function directly runs your shellcode, and then rest of things are all 0, and then that's why exchange AX is 0000, and that's why. So what I will do is break with main, then run it. So right now we are at here. So if I run this instruction, then EAX value will be 32, 0x32. And then we are invoking the system call because our debugger is quite smart. So whenever it misses the interrupt 0x80, it take a look at the EAX, and then that's how the debugger knows that this is get the EGID. And if we do next instruction for this, then the return value is 478. And let's check that. $1146. Then where that value comes from? 1146. So we invoke the get EGID. Operating system knows my GID, so it returns 1146. That's it. That's good. And then next, we need to invoke set regid. And then to do that, we can put the value on the EAX, then interrupt 0x80. But before that, we need to set the argument. And what we need to call is set regid. Something like this. And to do that, we need to set, this is set by EAX, EBX, ECX. So now we know that the EAX value stores the return value of this one. So we will put EAX to EBX, EAX to ECX. Then that's actually moving the value to the arguments and then call it. After doing that, we will also check make 32, do the object dump. So for someone who don't know about this command, like if you do the exclamation object dump, then it will rerun the same command with the same option. Yeah, so it's quite convenient to do so. So in that case, we will see that this is like get EGID, set the argument, set regid. Then we can check with the shellcode binary by the debugger. So run set a get EGID, we got it. And then move this value to EBX, move this value to ECX, move set regid to EAX, 0x47, and then invoke set regid, and then our debugger knows this system call syntax, so it also fetches the arguments. So you will see that we are actually invoking this kind of the functionality. And then if you don't want to use debugger, just want to see if it's correct or not, there is a program called strace. So I'm sure that you have experience with the ltrace that shows how the library calls goes in the level 1 of the week 0 or something, right? Week 1 challenges. So what strace does is like it will show that the list of the system calls that the program invokes. So just run shellcode. And then please ignore some of the upfront things, and then these are the things handled by the operating system and the library. But the important thing is we are calling the functionality correctly. Right. Yeah. Maybe I'm a bad teacher. Always let you know about the difficult, like the sophisticated step, and then always teach that like the simplest step later. Yeah. So this is how you can verify like whether it works or not. Yeah. So right now it works well. And then next step is invoke exactly. We want to do that. And then you can use these bytes. Copy and paste. Yeah. And then this is actually /bin/sh and 0. And then we will see how this kind of string building will work in the debugger. So we make it first with the debugger. break in main and run it. Then I will go one by one. So get Rudys ID, set Rudys ID, and then now we are at the point of the building the string. So take a look at the stack. This is a stack. And then low address, high address, so it's actually upside down. Yeah. I don't know why like early designers are not designed the stack starting from the low address. That will be more intuitive, but it's not designed that thing. So we need to always think about upside down and then upside down for the little endian. Yeah. So unfortunate, but we have to do that. Sorry about that. So it pushes 0, that means it will put 0 at here. So you see 0 at here, right? And then push n/sh. And then this one. Push //binsh. And then that's pointed by ESP. So if I examine a string bytes from ESP //binsh, and then //bin/sh and 0. That's how we can build a string. Yeah. And then now we know where that string is at. And then we will not using the address because it is thankfully pointed by ESP. So we will use that register to set that value. So what I will do is set EAX, set EBX as a //binsh, and then set ECX and DX are 0. And then system call. And then make 32. Now you have a full shellcode. Get EGID, set EGID, build a string, exec B. And then to test that, so it actually ran the shell. That's why it have like all these kind of thing. But you will see that get EGID, set EGID, exec B //binsh, null, right? So now you can run the shellcode correctly. And then after writing the shellcode, we do build make 32, it will automatically generate shellcode.bin. And then to actually interact with the challenge, you need to run this program, shellcode 32, the challenge binary name. Then it will get your shellcode from shellcode.bin, and then you can get the group ID from there. That's how you can solve the challenge and read the flag. Any questions up to this point? Then we will move forward to writing non-zero shellcode. Yes.
So if the binary already has that group ID set,
yeah,
why do you need to set it again?
So that's effective GID. And then when we are running binsh, a security functionality of the binsh is like it will remove all the effective GID. So it will ignore completely ignore them. So what we need to do is that before running that, we change it. Then they can never ignore. So that's why. And then in the some of the Linux distribution, they don't care about that, but the Debian-related distribution, including Ubuntu, yeah, they are all in that way. So in old days, like if you're attacking FreeBSD, you don't have to do that. Yeah, but then nowadays, like that's the de facto standard for the, I believe, almost all Unix distribution. So we have to do that. So this is a non-zero shellcode. No, this is a shellcode with the zeros because
in object dump, we can see a lot of zeros. Okay, and then we need to remove that to make our shellcode to be acceptable by the string-related functions. Then let me work with the non-zero shellcode 32. Then to do that, copy all the things, shellcode template to here, and then I will overwrite shellcode.s file with the previously written one. Because I will just start off from that one. So we have all those files, but I will just using like the shellcode with the 0 byte. In that case, the challenge program complains about, oh, your shellcode has 0. It will not be accepted. So we need to remove all 0 bytes. Then from the object dump, we need to remove these zeros at the first place. Then let's think about how we can put 32 without 0 at all. And then easiest way to do this is push 1 byte and pop. And then the reason why this works is that Intel CPU is backward compatible. And then that is designed with the 8-bit, 16-bit, 32-bit, 64-bit, and then they still have 8-bit instructions. So that we are actually using 8-bit instructions to push 1 byte. There will be no 0. And then, but even if we push 1 byte, 32-bit machine will push 4 byte. This is very weird, but it works. Yeah. So I'll just change like the push this value and then pop to the EAX. So we are actually using stack to push the value and then pop it. Then let's see how the disassembly or opcodes are different. No 0. Push 32, pop EAX. Even shorter, right? So this is one trick. Easy. And then for the second 0, we can do the same thing. Push 0x47 and pop, right? So here, did it again. No 0. Right? And then next is push 0, but we know that this can replace push 0. XOR EAX, EAX, then EAX will become 0. Push 0. No 0. And then those kind of move, we can actually push, pop, right? So for this one, push exec V, pop EAX. And then for these ECX and EDX, so we don't have to set it in order. Just remove this. Then we know now EAX is 0, right? Move 0 to ECX, move 0 to EDX. Then set EVX and 0x80. Is there any 0 bytes? No, it's clean, right? And then let's test it again. It runs it correctly. Yeah. After that, you can run the challenge binary. Then you can get the group ID. So this is not difficult at all, right? Yeah, it's very simple. Yeah. And then you will have all the tutorial code in our calendar and you can download it. And then you can also have a video. So that don't worry much about that. Any questions? So I already did that. So non-zero with the like the 0, 1, opposite way. Yeah, that definitely works. And then let me do that. I'll just copy shellcode.bin into this one. Because it does not have any check. The other challenge is like 0 byte or something. So because like we will mainly use non-zero shellcode. That's why that's important. And then if you want to go straight down, and then you can write alphanumeric shellcode and then solve everything. That's also possible. Then let's move on to the 64-bit. And then I will not cover shellcode 64, directly go to the non-zero 64. Yeah, because we will eventually do that. And then if you do that, then shellcode 64 is free. So let's go for the non-zero shellcode 64. From the template, we copy all. Yeah, and then. So I also put some of the important thing for the 64-bit. So please keep that in mind. Syscall numbers are different. So if you need to use the number, then you need to be careful. But if you need to use symbol, then you don't need to worry about that. Compiler will automatically fetch the right header file, so they will have the value. And then different thing is like that it's not about the int 0x80 anymore. We need to run syscall. And then another thing is like there's no 8-byte push. So we did the 4-byte push to build a string. But if we do that, 4-byte push will actually push 4-byte and then 4 more zeros in there because it's a 64-bit. I don't know why it is designed that. Maybe CPUs are not designed for hackers. That's why. Yeah. So what we need to do is like we can move 8-byte immediate value to one of the register. And then if we push this, then it will push 8 bytes. So one of the way to build a string is like the push 0 and then push this kind of register. So we will basically do that. Then first thing is like we need to call get EGID. Then let's do the same thing. RAX, because it's a 64-bit, and then this call. Not int 0x80. Then let's check. Make 64. Do object dump. So push 6C, pop RAX, this call. And then the reason we have like the same opcode here is like Intel CPU, thank you. They are backward compatible. Yeah. And then hold on S-tray shellcode, then it run get EGID correctly. And then next is calling set regid. This is how we can invoke, but before that, we need to set the arguments, and then this actually overwrite the RAX register, which stores the return value. So we need to set the argument beforehand. That's why. So move RAX to which register stores the first argument? RDI, right? Then what's the next? Yeah, right. Then that's how we can set the registers. Make 64 and then object dump. Work something like this. No 0. And then as trace shows that it calls it correctly. And then important thing is like you need to take a look at the return value. So for the operating systems, if something does not have the return value, if they return 0 means it was successful. Non-zero, not successful. But that does not apply for this one because we expect like some return value for that. And then after that, we need to run execve. And to do that, and then I will show you some other trick. So here, I will introduce a very weird trick. And then you can get a 0 with 1 byte. And then how can you do that is there's an instruction called the CLTD. And then what it does is like it exists there for handling a double precision value or 8-byte integer in 32-bit architecture. So in 32-bit architecture, all the registers are 4 bytes. And then how can he operate on the 64-bit integer is that there is a notion that the Intel CPU can use EAX and EDX as a pair to operate on a 64-bit integer. And then what CLTD does is asserting that, oh, we want to use EAX and EDX as a 8-byte integer. And then it will move the value in the EAX to there. Then think about it. We push 6EXECVE, pop RAX. Then RAX value will be 3B, 0000003B. And then if we run CLTD, then there might be 00000000003B as a 64-bit integer. So what that means is that your EDX or RDX will automatically have 0. And then I will show that. Make 64. GDB on shellcode. This says on main, and then I will break it here. Min plus 19, then run it. So right now, RDX has this kind of weird value. We don't care. But we set RAX as a 03B. But the CLTD instruction will make the RAX and RDX pair as the same number with the RAX. So it should clear RDX as a 0. Right? So you can freely get RDX 0 with 1-byte instruction because CLTD opcode is 0x99. Yeah. So with only 1 byte, you can get a free 0. Yeah. I'm giving a hint for how you can write a short shellcode. Yeah, using this. And then definitely short shellcode should never have 0. Yeah. That's the thing. Then now we know that the RAX is 0x3B. And then RDX is 0. But what we need to do is RDI should be this one. RSI would be 0. RDX 0 to invoke EXECVE, but we already met RDX is 0. And then to met RSI as a 0, so they actually pop RAX actually set RAX as a 3B. CLTD sets RDX as a 0, and to set RSI as a 0, just move RDX to RSI. And then we need to build a string and put that onto RSI. To do that, I'll just copy this. It's like a / /binsh to RBX. And then the reason why I use RBX is like It doesn't matter because we don't use RBX for the system call at all. Yeah. So we can freely with the messing with the RBX, that's why. And then we push RDX first because RDX is 0. Push 0 and push RBX. So that's actually 0 / bin sh. Then now RSP points to there. So we will move RSP to RDI. And then syscall. And then let's take a look the entire instruction by instruction. Make 64 and then percent. Then GDB shellcode, the main and run it. So the first 3 instructions are get EGID, and then I got the same value 1146, right? And then move those 2 values to RSI, IDI and RSI, and then put the system call number to RAX. Then we can set RegID. And then push 3B, pop RAX. So we have a RAX as a 3B. And then CLTD will make RDX as a 0. And then we will move RDX to RSI to set that 0. And then we will move complete 8 byte value, we have no 0, to RBX. And then we cannot move RBX directly to RDI because this is not an address. So we need to put that on memory. To do that, we push RDX first to push 0 on the stack, and then push RBX, push / bin sh, and then because that is pointed by RSP. That's a string / bin sh, and then put RSP to RDI. Then it says exec b bin sh 00. So I run it, then we can get the GID. I will take your question a little later. And then if you do object dump, you will see there's a no 0 at all. Question.
Is there a reason why we can't do XOR RDI?
Oh, you can do that.
Okay.
I just want to take the shorter route. Yeah, XOR IDR RDR 2 bytes. CLTD 1 byte.
Well, I'm saying for the second part, like
Yeah.
after the CPL and the
Yeah, you can do that too. And then you will see that this. So if I move RDX to RSI, that's 3 bytes, right? No. I will show you like how we can reduce more bytes. So set the RDI and RSI value same. It requires 3 bytes. Let's make it as 2 bytes. How you can do that is very easy. Instead of move, I will just use a push and pop. Same, right? Two bytes. Yeah, that's how you can reduce bytes in your shellcode. And then another thing is like the for short shellcode 32 and 64, you don't need to include the set regid get egid. I already do that for you. So that you only need to focus on running bin sh. That's why you can get it to further like a 2 bytes or something. Yeah, that's the thing. Any questions? Then please write your shellcode and then feel free to ask any questions to our TA Lucas and myself.